The final topic of this notebook is the definite integrals by substitutions. So how does the definite integrals differ? Let's look at this example. This example can be done by substituting u as sine of theta. And then in the end, what do? If you plug in u equals to pi over 2 and u equal to 0 and subtract one from the other by fundamental theorem of calculus, you're going to fall into trouble. What you need to do is to do one of the two. First, completely finish the antidifferentiation and then plug in theta equals to pi over 2 and theta equal to 0 and subtract one from the other. Here's substitution, y as sine of theta, and then the derivative is cosine, and then d theta is 1 over cosine times dy. And then the integral becomes like this. Sine squared is y squared, and then cosine theta, numerator and denominator, they just cancel each other out, and what we have this antidifferent, we have this antiderivative, 1 over 1 plus y squared dy. What is 1 over 1 plus y squared? That's the derivative of the arctangent function, so the antidifferentiation yields arctangent of y. Plugging the original variable back in, we have arctangent of sine of theta. Now we are ready to plug in theta equal to pi over 2 and theta equal to 0 and subtract one from the other to calculate the definite integral. So plug in pi over 2, plug in 0, so we have arctangent of sine of pi, which is 1, minus arctangent of 0, so what do you have? Pi over 4 minus pi over 4 minus 0, so we have the answer, pi over 4. This is one way. This works pretty well in Calculus 1 level and Calculus 2 as well, but if you move on to multivariable, there will be some situations this method will break down. So personally, I'd like to encourage a second method a little bit more, especially to mathematics majors who will have to go to higher level mathematics. So how do we handle this method? First step is the same. Y is sine of theta, and then all those derivative and then differential computation, and then adjust the starting and ending point of the integral. Theta is moving from 0 to pi over 2, and y is sine of theta, so it is moving from sine of 0 to sine of pi over 2. So y is moving from 0 to 1. Consequently, after substitution, the definite integral from 0 to pi over 2 cosine of theta plus this definite integral becomes y is moving from 0 to 1 over 1 plus y squared dy, like that. So antiderivative of that is arctangent of y, and then plug in y equals to 1, y equals to 0, subtract 1 from the other, and we have the answer. And this method remains valid all the time, and this is not particularly harder than the other one. Therefore, personally, I'd like to recommend the second method to everybody. And well, in Calculus 1 or 2 level, it's okay because every problem in this level can be done in both ways. Okay, here are a couple of more examples. Area computation. And area computation can be combined into definite integrals. Integration by substitutions. And then this is one of those. And then how do we solve this thing? Well, area computation from -1 to 1 will not be a good idea because we want to find a shaded area, but this part will give negative, that part will give me positive, so they'll cancel each other out. Better idea is to get the integral from 0 to 1, only this part, and then double it. By symmetry we can do that. And we're going to end up with this computation. Double the integral from 0 to 1, x 1 over square root of x, like this. And then this is going to be a typical integration by substitution problem. Inside will be u, and then this is appropriate computation. And then I like the second method better because it works all the time, so I'm gonna stick to the second method. So change up starting point of the integral, x equal to 0, so u is gonna be 1. X is moving from 1, so that's 1 minus 1 squared, so 0. So the integral becomes u is moving from 1 to 0. And then after the substitution, we get this kind of integral. And then after antiderivative computation, applying the fundamental theorem, we get the answer. Another example. Okay, we have plenty of time to do another example. Okay, how about the next example? A little bit tougher integral. Okay, looks like let's take a little bit longer time here. Similar problem. Integral is gonna go from 0 to 1, and then we're gonna simply double that, because if you go from -1 to 1, we're gonna have cancellation. That's gonna be a problem. Alright, actually I didn't write any solutions, so alright. Okay, let's go ahead and do that. So let's copy to make this a little bit simpler. So the first step is going to be the same. We have to find out, as a matter of fact, I didn't copy enough. Okay, let's copy that one. Okay. So this is the integral we are calculating. The first step is the same. U is the inside. The derivative du dx is, of course, -2x. And then dx can be calculated at 1 over -1/2x times du. Now, if I plug everything into this definite integral, as a matter of fact, before plugging in, let's adjust starting and ending point again. When x is equal to 0, then what do you have? U is gonna be 1 minus 0 squared, so that's 1, isn't it? Okay. What if x is 1? In that case, u is gonna be 1 minus 1 squared, so that's gonna be 0. So the integral will be starting from u equals to 1 and u equals to 0 instead. So this is the integral computation we are doing. 2 was there before, and then 2, and then the integral u will be going from 1 to 0, as we did here and there, and then this will be substituted into u, and then dx will be substituted by 1 over -2x times du. Now, do you see cancellation? Yes, there is some cancellation, but I'm afraid not complete. Let's see, this 2 to cancel out, we have just negative sign, so this can all go. Negative can go, and this x in denominator will cancel out one of those cubic, and you're gonna get x squared. Now what we do, we still have some x left out, so we are in a bit of a trouble, but please remember that u is 1 minus x squared, so from here I can find x squared is 1 minus u. So I can replace this one by 1 minus u, and finally we are ready. This is a u integral, and then we can complete the computation. From this point on, everything is just going downhill. It's going to be easy. So distributing, you're gonna get just u to the 1/2 power, and then u times square root of u to the 3/2 power. Okay, now we are ready to apply the antiderivative formulae, the power rule actually. So add 1 to the power and then reciprocal. Add 1 to the power and then reciprocal. Oops. Does it look right? Looks like everything is okay. And then let's put starting ending point 1 to 0. So minus, we have to plug in u equal to 0, and that's going to be just 0, easy to calculate. If I plug in u equals 1, that's going to be 2/3, and then minus 2/5, and then this negative was there before. I hope everything is correct here. So what do you have? This minus minus becomes positive. We have just 2/3 minus 2/5, and then what is the simplification? That's gonna be 10/15, maybe minus 6/15. Is that right? Looks like it. So I'm gonna 4/15, and then is that the answer? Yes, that's the answer. Okay, there goes a comprehensive problem actually. We had to get the area formula straightened out using the property of the definite integral. You can separate this part, that part, and then positive and negative may cancel out. You have to use substitution, and then I like to use the second method because that works all the time, not in selected states. So u is moving from 1 to 0 instead, and then we have to substitute everything in, but there's some residual x left. How do you handle that? Go back to the original substitution and then express x squared as a u expression, 1 minus u, and then just go ahead with antiderivative computation. Expand out, apply power rules, apply fundamental theorem of calculus, and then some computation.